Okay, so yesterday we kind of finished up all our discussion on LDPC block codes, and today we're going to focus on spatially coupled codes, which are LDPC convolutional codes, just the convolutional version of LDPC codes. And I list here, the previous set of slides was prepared by David Mitchell, and this work is based more on some tutorial type talks that we've given on spatially coupled codes over the last several years, and there's several collaborators that have worked on this along with myself. So what's an LDPC convolutional code? Well, we saw when we discussed convolutional codes the other day, we didn't discuss the parity check matrix directly, but we discussed a generator matrix, and we saw it had kind of a diagonal-like form. Remember, the top row was shifted down like this. And if you look at the parity check matrix of convolutional codes, they also have a diagonal-like representation. So this goes back to work by Jimenez, Fellstrom, and Zgangarov in 1999, the first ones to really look at making low-density parity checks codes out of convolutional codes. So they just looked at it this way. For a rate B over C code, these submatrices are all C minus B by C submatrices. And this notation is going to change later in the talk. So, but for now, it's C minus B by C. Okay, so it's kind of the usual. C minus B is kind of the number of checks in a given row here, and C is the number of variable nodes connected to a given column. The M sub S, so each row, the other parts of this matrix are all 0 because it has the diagonal form. Each row here has a certain width, and the number of submatrices in a row is M sub S plus 1. M sub S is called the syndrome former memory. So it's the maximum width of the non-zero area of this matrix counted in submatrices. Now remember, when we talked about convolutional codes, we talked about the memory. And that was with respect to the generator sequences or the generator polynomials of the code, the way we encode the code. Again, here we're talking about defining the code in terms of the parity check matrix. This is a very similar concept, the syndrome former memory. We talked in the block code section about forming syndromes, okay? So you can do the same thing with the convolutional code. You can take the receive sequence, multiply it by the transpose of this matrix, and you get a syndrome, okay? So for that reason, this is sometimes referred to also as the syndrome former matrix. And the width of the parity check matrix here is the syndrome former memory. So it's a very similar concept to the memory order of a convolutional encoder. The constraint length is just the same width, except we count it in symbols rather than in submatrices. So now, this is a kind of a very general view here in the sense that the submatrices in general, we're allowing them to be time varying. Okay, the structure stays the same, but the individual elements in the submatrices can be time varying in general. Now, if there is no time variation, then it's a so-called time invariant code, which is the kind that we would be familiar with seeing from our discussion of convolutional codes. We did not talk about any time varying codes in that case. But with low-density parity check codes, there's no reason why the codes have to be time invariant. It's not a particular advantage, so to speak. And also, if the submatrices repeat with some period t, then they're periodically time varying. And here's where everything I've said so far just any convolutional code can be described this way. Okay, the codes we were describing the other day, they can all be described from this point of view, from the parity check matrix point of view. What makes them low density? Well, the same thing that makes a block code low density, a parity check matrix for a block code. If we have, say, for example, J1s in each column and K1s in each row, then we refer to it as a JK regular LDPC convolutional code, assuming that J and K are small integers. The memory is very large. Yeah, with LDPC convolutional, again, just like with block codes, LDPC codes are powerful codes. They're big codes, and as we talked about the other day, when we have convolutional codes, if we want to make it a powerful code, we've got to have a large memory. Okay, and that would be reflected here from the H matrix point of view in the large syndrome former memories. You can also have irregular LDPC convolutional codes. They're actually not as interesting. We'll maybe, if I remember to say it, mention why later on. But the regular ones are the ones. Remember the real purpose of looking at irregular codes was that the regular block codes didn't have good thresholds. So we had to make them irregular in order to get good thresholds. These, by their very nature, have good thresholds. So we don't really have to you can make them irregular, but there's not the same motivation to do so.
Now the time varying, can it be viewed like irregular? Because you could actually bring irregularity by...
Yeah, I mean, whether it's time invariant or time varying, you could make it irregular. Yeah.
But the time varying aspect can bring the irregular aspect, right?
Still regular, right. Just fixing the weights of each column and row. Now, one way, this is more the historical view. This first hour here is going to be more the historical view, the way we started looking at LDPC convolutional codes in the early 2000s. Before we took this more modern view, which we'll start talking about in the next class, having to do with coupling together sequences of graphs. So the original way that Jimenez, Feldstrom, and Zagangorov envisioned constructing these codes was just taking an LDPC block code and doing an unwrapping process. So you take a good LDPC block code and you unwrap it, and you can get a good LDPC convolutional code. So for example, here's a little rate 1/2, 3/6 regular LDPC block code with n equal 10. Again, because n is only equal to 10, it's not really low density in this case, but okay, the idea is we would be working with an H matrix, maybe 3/6 regular of size 1,000 or something like this. So you can actually cut it along the diagonal here like this, take this upper part and flip it down here and paste it down there to get a diagonal type of structure to the matrix, and then you can just take this and repeat it indefinitely. In general, you can think of this going in both directions as being bi-infinite. Of course, in practice, we start at some time and would end at some time, but at least initially, we don't have to think of it that way. So you get, and the unwrapping process preserves row and column weights. So if this is 3/6 regular, this thing will also be 3/6 regular. This thing just flips down here, and then it's repeated. So it's clear to see that the column weights are all preserved and the row weights are also all preserved. So, and the convolutional code rate is the same as the nominal block code rate. Again, why do I say nominal? Well, if this was constructed randomly, for example, it may have a dependent row or two. So the actual rate could be a little higher. But the nominal rate of this thing is a 1/2, and the convolutional code would have the same rate. So here's an example. I think it's the same code. So we have the little submatrices in this example are just little 1/2s. So the rate then, B over C, is just 1/2. Okay. The width of a row in symbols is 10, so that would make our constraint length 10. The width in submatrices is 5, so that makes the syndrome former memory 4. So there's MS plus 1. The column weight is 3. I mean, this is the same example we had from the previous slide. And the row weights are all equal to 6. So this then, we had a 3/6 regular LDPC block code. We do this unwrapping process, and we get a 3/6 regular LDPC convolutional code. And the parameters, the constraint length, when we do this, the constraint length is always, of the convolutional code, is equal to the block length of the block code that we started with. So if we start with a block code of length 1,000, we're going to get a convolutional code with constraint length 1,000. So these are big convolutional codes. We're not decoding them with the Viterbi algorithm. We're not decoding them with the BCGR algorithm, so we don't care how many states they have. Okay? We're not decoding them on a trellis. So again, we can get irregular if we want. In general, if you use this process, you get periodically time-varying codes. I think you can kind of see that just from the repeat. You know, when you repeat here, you're going to get like periodically time-varying. So these rows can vary in time, but then they'll repeat. So here's a kind of here's kind of a view of this from the graph perspective. This is a LDPC block code Tanner graph. I think this is the same one again. We've got 10 variable nodes and 5 check nodes. Okay. And if we go through the unwrapping process, we get a bi-infinite graph. As I said, you don't have to think of this as being terminated on either end. You can just think of this diagonal as going infinitely in either direction. And you get a graph that looks like this from this unwrapping process. And this would be the Tanner graph of the corresponding LDPC convolutional code. Now the connections don't look exactly the same because you did this cutting and pasting, and that kind of changes the connections a little bit, but it basically has the same properties. So if you have 10 variable nodes in your original block code, you're going to get 10 variable nodes in a constraint length here, which I've drawn a little box around of the convolutional code. And that basically means that nodes here can talk within one iteration, can talk to another node within a constraint length. Okay. To get further, to talk to a node further away, you need to go to more than one iteration. So this node, I think, can come here and talk to this guy within one iteration. But he can't talk to anything out here without going through at least 2 iterations. I'm sure it's got 4 cycles, yeah, because it was just a small little code, yeah.
Can you guys do analysis of the cycles?
Sure. I mean, when we construct codes randomly, for example, we would use a construction method which at least guarantees no 4 cycles. For one thing, you can show that when you do this, when you unwrap a block code, any cycles that existed in the block code, you're not going to create new cycles with the unwrapping process. So the short cycles in the block code will either still be there in the convolutional code or they'll be broken, which is a good thing. Okay. So the degree 3 variable nodes in the block code, again, we have degree 3 variable nodes down here in the convolutional code through this process, and degree 6 check nodes here and degree 6 check nodes down here. So this is just from the kind of from the graph point of view what we looked at on the previous slide. Any question on this? So you can do, this is a different kind of construction. Actually, when I first got involved in working on LDPC codes in the early 2000s along with Michael Tanner, we had looked strictly at quasi-cyclics. And this is kind of a different way, a different kind of construction. We wind up with time invariant codes in this case. So you can look at an H matrix in this case, which is, this would be a block code. It's actually a 2-3 regular block code with block length 21 if these are these are all shifted identity matrices of size 7. And you can, the graph for this thing is like this. And if you replicate this graph in time, you get a rate 1/3. In this kind of construction, you do wind up with time invariant convolutional codes. The constraint length is 21. It's again the number of the block length of this H matrix. And the MS in this case I think is 6, okay? And the idea here, well, okay, you get this by, no, we didn't do this through this unwrapping process. We just took this graph and replicated it in time, pasting them together, and you get the convolutional version of the graph. Now, if you look really carefully at this graph, I think you'll see that it doesn't actually replicate this. And the reason is we took the picture out of this paper, which was our original paper on this. And in producing the convolutional graph, we had reduced this H matrix to a simpler form. Okay, so the graph that we have here actually is from a reduced H matrix. And I think the constraint length here is actually smaller. The original thinking of, you know, people who work in convolutional codes, one of the things they want to do, and it's always thinking from the point of view of the Viterbi algorithm, say, or the BCGR, is you get a code and you try, we did talk about this a little bit, I guess. We try to get a minimal encoder. You have a code and you try to get an encoding matrix which is minimal, so you have the fewest number of states possible. So that's actually what we did with this thing. We took it and we got it in generator matrix form, and then we minimized it, and that's the graph that we show here. And if you look carefully at this, you can see the memory is less than 6. I think it's 4 or 5. But actually, the way you do this is just one slide. There's a lot in this. Each of these identity matrices can be expressed as a monomial, a power of D. So you get like an H of D parity check matrix, which is in the transform domain, just like we had G of Ds for the generator matrices of convolutional codes. And then you can go backwards from H of D to G of D, and then you can reduce that. If you go directly backwards, you're going to have, with this I sub 6, it corresponds to a D to the 6th power. And if you go directly backwards, you're going to have D to the 6th power and G of D, and you're going to say, okay, that's memory 6. But you can reduce that and get a smaller memory that encodes the same code. So anyway, that's a detail, but I just want to point out, if you look carefully at this and try to see that its memory is 6, I think you'll be disappointed. Okay, so it does have C equal 3, and I say here that the memory is 6, but I think that's actually not correct. Okay. You can go from here to here and then from here, but that's only 4 time units rather than 6. Okay, so this again is the unwrapping type of thing, and if we do simulation now, so you may say, all right, well, that's interesting. You know, how do these things perform? Well, here's the simulation comparison. Now, this is for a block length of 4028. It's not for this code. It's for an LDPC code of block length 4028. And we did this unwrapping and turned it into a convolutional code. And here's the bit error rate performance of the original block code at 10 to the minus 5. It requires about 1.8 dB. Remember, the threshold was about 1.1 dB, so we're quite a ways away from threshold, but we would expect that because our block length is not so big. Okay, we take this code, unwrap it to a convolutional code of constraint length 4028, and we get what we called a convolutional gain of about 0.6 of a dB in this case. So these are good codes. Otherwise, is what you could draw from this one picture is that if you do this unwrapping process of a good LDPC block code, you'll get another good code, and you'll have some gain. Now, I'm going to talk more about later, is this a fair comparison? To compare these two, it seems like it because one's just derived from the other, but it's not really because the decoding latency here is higher than it is for this. But we'll get to that later this morning or this afternoon. There's efficient encoding for these kind of codes in the sense that you can The diagonal structure, along with the sparsity condition, gives us a simple shift register-based systematic encoder. So for a rate 1/2 case, JK regular, we can have information bits coming in here. Each information bit is sent out in systematic form. And then we switch down here and pick up a parity bit. And we have a shift register here, which is just connected according to these are the coefficients of a row in the H matrix. If it's a time-varying code, then these are time-varying. But if it's a time-invariant code, these are fixed. Okay, and for example, in this little example we've been looking at, a row of H would be like this. So we'd have connections in these. I didn't show them all here. There's one more here, I guess, and then another one in here, and then this one, and then finally the last one over here. There's going to be 6 in each row, so there'll be 6 taps off the shift register. Well, 5 plus this connection. So you can encode actually. Encoding complexity is actually independent of the constraint length because it's JK regular. So you always have only K taps active in encoding any bit. And in order of terminology, this is basically order of 1. This would be the same thing as what we talked about yesterday when we looked at yesterday afternoon when we looked at the way we would encode LDPC block codes with that lower encoding, lower diagonal, lower triangular matrix. And when we did that last part of the encoding with the P2 part, the second part of the parity bits, we were just reading off the ones in the rows of the H matrix. And if it was JK regular, there'd be K ones in each row, so that's exactly the same complexity as doing this. Okay. Now the nice thing here is we don't have that little, in general with the block codes, we had that little G by the last G rows that had to be encoded with higher complexity. There's also a constraint on the H matrix that has to be satisfied in order to do this. Okay, generally you can form an LDPC convolutional code, and there has to be a certain condition satisfied on the lowest order terms actually over here at this end of the rows of H. You have to have 1s in order to be able to do this. So this is you could say, well, yeah, it's not quite random then if you want to ensure that you can encode this way, and that's true. You could have a big code, and you have to make sure that the first C bits in a row of H always satisfy that first little submatrix has to have full rank in order to do this. So you could say, all right, I'll construct a random code, and if that little submatrix doesn't have full rank, then I'll put a 1 in there or something, whatever I have to do to give it full rank, and then we could encode this way. Okay, but again, once you I mean, that could affect, although it's not likely to affect the performance much, but it's a little, once you get away from the randomness, your guarantees are no longer there. Okay. Anyway, the encoding normally can be quite simple. Now, what about decoding? Well, again, let's think of it as being bi-infinite for now. There's a time index associated with the nodes, which is really different. With block codes, we don't have the notion of a time index. All the nodes are there. We receive everything at kind of one time, and everything is iterated at the same time. Here, there's a sequence of iterations that we go through to decode. So but the node connections, because of the convolutional structure, are localized within one constraint length. And this again is an example of this is a rate 1/3 code with memory 2. And the original decoding idea that appeared in the original paper that we talked about was it was a decoding architecture designed for high-speed parallel operation. And since in one iteration nodes can only speak across one constraint length, the idea was to use if we were going to do I iterations, we would use a set of I processors. Each one would cover one constraint length, and they would all be identical. Okay, in the unwrapping procedure, each constraint length is a replication of the previous one. Okay. So every one of these processors would be identical, and they would cover exactly one constraint length worth of nodes. And so it could be implemented in parallel. Otherwise, while you were doing, say, an iteration here on these bits, you could at the same time be doing an iteration over here on some other bits, okay? Because these are not going to talk to these during the same time with a different processor. So this is a nice architecture if you want to do high-speed parallel processing, decoding of these codes. So each time a processor is looking at a constraint length, it does just two things. It updates the check nodes on kind of the way I've drawn it here on the far left end. For large constraint length codes, these could cover a lot of nodes. And then it updates the variable nodes on the right end. And then it shifts over by one position, or you can think of the variables as they're received shifting through the processor. So each time, so a variable node may shift in here. It shifts in here, say from the left. The first two times it's in the processor, it doesn't get updated. It is involved in updating the nodes that are being updated, but it gets updated as it's about to leave that processor. And then when it's in the next processor, it gets updated a second time. And it gets, after it goes through all I processors, every node has been updated I times. And when it exits the ith processor, then we decode. So we would, when these bits exit the ith processor, these are called target symbols. They're the ones that we're decoding at a particular time, and they're decoded. And then at the next time, the bits are going to shift, and these would be decoded the next time. They'd get their ith iteration and be decoded. So this shows the next time unit, and again, then we'd update check nodes on the left, update the variable nodes on the right, and then do this decoding of these target symbols. So that the sets of C symbols are decoded each time unit, C symbols at each time unit. Now this requires that you do a fixed number of iterations, and it also requires that there's a total delay of this amount in decoding. Otherwise, bits have to enter over here, and they have to go through I processors, each of them containing ms plus 1 time units. So there's a total delay of I times ms plus 1 time units, or I constraint lengths, before you start to decode. If the constraint length's big, that's a large delay. Okay, and that's one of the reasons for, basically the reason for that performance gain. Any question on this? Well, I'm not sure what you mean. I mean, these symbols shift. These are the received symbols here, so they have their LLRs, and they shift into the processors. They're in a particular processor for ms plus 1 time units. They just shift one time unit at a time, and they're updated here when they're about to leave a processor. And then totally they're updated 10 I times. Any other questions? So this is it's a convenient parallel architecture, particularly since these are identical processors. I mean, one thing you can argue is that in terms of processor complexity, since the constraint length is equal to the block length of the block code that we unwrapped from, this processor would have the same complexity as a processor that it's a decoder, if you want, BP decoder, that we would have for the corresponding block code. So there's some correspondence between the complexity of a processor is the same for the original block code and for this derived convolutional code. Now you need I identical copies of this processor, okay, and you need a larger delay here. Now, one thing that the delay, however, it's that delay, it's nice for the architecture, but it's not necessary for good decoding. So a variation on this, which was originally published as an algorithm by Iyengar and Paul Siegel and Jack Wolf back in 2012. We had previously used a version of this to do density evolution on LDPC convolutional codes. But the idea is, instead of using, if you look back at this pipeline, you've really got it stored in memory, you've got I constraint lengths stored in memory. With the window architecture, you store many fewer symbols in memory. Okay, typically just a few constraint lengths. If you do this, let me just describe how it works first. So you could say I have a window, and you're going to apply the standard belief propagation flooding schedule throughout the window. You can use different kinds of schedules too. We didn't really talk much about scheduling. So just think of it in terms of your standard belief propagation decoding within a window. And then you decode the target symbols at the end, and then you shift the window over. And you do flooding here, and then decode the target symbols at the end, and then you shift the window down again. The window, in order to get good performance, the window size is typically just a few constraint lengths. So with the pipeline architecture, it was fixed at I constraint lengths, where I is the number of iterations you want to do, which is kind of an unrelated thing. It is that way because you want to get this parallel architecture. But typically, you don't need, typically if you want to do a lot of iterations, you really don't need to store that much in memory. So the storage requirements here are much less, and the latency is much less. It's only a few constraint lengths rather than I constraint lengths. A fairer comparison to block codes in terms of latency and memory requirements in the decoder would be to compare with a block code of this size. Maybe a few constraint lengths of the convolutional code you're comparing to. And we'll show comparisons like that later. So any question on this idea then? I'll come back to this, and we'll kind of view it again from this more modern kind of view of LDPC convolutional codes. Yeah.
There's still a delay associated with each shift of window, right?
Yeah, I mean these bits enter the window at a certain time, and they're finally decoded. It would be however big the window is, that many time units later, and that's usually a few constraint lengths. I mean, it's a parameter which affects the performance of a code as to how big, or of the decoder, as to how big this window should be. And we've done quite a bit of work on that. Some of those results I'll give later today. Anything else at this point? So again, back to this picture. Why do they perform so well? So here's one initial way of looking at this. We'll have a lot more to say about it next class. Remember, we looked at these structured LDPC block codes where we would have M by M permutation matrices, blocks of M by M permutation matrices. Or if we wanted to make it quasi-cyclic, they would be M by M circulant matrices. So we can do a similar construction with LDPC convolutional codes. We start with this diagonal structure, but we put little subblocks in here that are permutation matrices. So we can get an ensemble this way. In this example, we have the total number of the width of the non-zero part of a row here is 6 of these submatrices. This would give us a 3-6 regular structure. We have 3 vertically and 6 horizontally. And so the constraint length then would be 6 times the size of the permutation matrix that we use. Okay. In this little example, it's shown as 4. Now, one thing to notice about this, and we'll say more about this later, I had started out saying, let's just think of this as bi-infinite. So this is going to run backwards in time, too, this diagonal matrix. And then So if there's no termination at the ends, every row has weight 6, every column has weight 3. But of course we know in practice we have to start at some time, and eventually we have to end. So there is termination, there's a start point. And if you look at this matrix, it's a 3-6 regular matrix. But if you look at the first 2 sets of rows, the first set of M rows has only 2 1s in it. Okay, and then the next set of rows has only 4 1s in it. Again, these are permutation matrices, so they all have row weight 1 and column weight 1. It's not until we get to the third set of rows that we have the regular structure. And then that continues on. These are typically long sequences that are encoded and decoded with this type of code. So it has they're built on essentially a regular structure, but there's a small, or what we like to call a slight irregularity at the beginning of the graph and at the end of the graph if we terminate at the other end. So the variable node degrees never change. They're 3. But the check node degrees at the beginning and the end are smaller. Okay, they're 4 or 2. Okay. So that gives us, I mean, that is a hint. We'll talk about this more later. It's just an observation at this point. But that is something that allows the decoding to converge to the correct code word. It gives it an advantage over a purely regular structure. So when I say these are regular codes, we're cheating just a little bit in that we've entered a slight irregularity into the design. But it's not, the basic design is still regular. So in terms of implementation complexity, it's not like what you would have to go through to implement a general irregular code with all kinds of different degree distributions and everything. It's just a slight irregularity at the beginning and the end. And basically, in a sense, that's all you need if you use this kind of structure. We developed some distance bounds. If you consider the ensemble of LDPC convolutional codes with permutation matrices, constructed with permutation matrices, the ensemble of all possible codes, it can be constructed this way, just like we talked about with the block codes yesterday. You can get bounds on the minimum distance, or in this case, since it's a convolutional code, the free distance. And just like we had with the block code case, the Gallagher results for 3.6 and 4.8. Okay, these were the block code distance growth rates. This was the Gilbert-Varshimov bound for rate of half. And this is kind of the ratio of the Gilbert-Varshimov bound was 4.7 times the growth rate of a 3.6 regular block code, but only 1.7 times the growth rate of a 4.8 regular block code. So as we talked about yesterday, as the density of the block code increases, the codes get stronger. Their minimum distance properties get closer to the Gilbert-Varshimov bound. And we get the same thing, we can derive the same kind of bounds on free distance of the permutation-based ensembles of convolutional codes that we just talked about. And we get these results for the free distance for 3.6 and 4.8. And we get similar ratios between the distance growth rate of 3.6, free distance growth rate of 3.6 regular convolutional codes and 4.8 regular low density convolutional codes compared to the bound for the general class of convolutional codes. So again, 3.6 regular is about a factor of 4 away from lower growth rate, and the 4.8 regular is only a factor of 2 worse than what you could get with general codes. Again, this is the penalty that we pay for the low density structure. It gives us linear decoding complexity, but we pay some penalty in terms of minimum distance compared to just the general class of codes. So the purpose of this is just it's very analogous to what we get in the block code regime when we use these kind of random ensembles in terms of distance properties. Okay, we can do the same kind of random ensemble analysis with convolutional codes, and we get analogous results with regard to distance properties. Any question on that? Well, if the density, as the density gets larger, these distance ratios get closer and closer to the bounds. And yeah, I mean, I think I have a graph later on. This is a graph that we did we did this 10 years ago using an analysis technique that was a little cumbersome. That's why I only showed 2 values here. It took forever to evaluate these things. But once we started to work with protographs and the weighted enumerators from protographs, it's much easier to get these same results. And I've got another picture later that shows a bunch. But you know, if you increase the density, if you go to 510, you're going to be out in here. If you go to 612, you're going to be here. If you go to 714, you're going to be, I mean, you'll get there pretty quickly. But then you lose the advantage of implementation complexity. You're increasing your complexity when you do that. Of course, distance is just one thing we want to look at, and the other thing is thresholds, iterative decoding thresholds. And we've done these for the block codes, right? These are just the 3, 6, 4, 8, and 5, 10 regular cases. And here's the block code thresholds that we showed previously for the erasure channel and for the Gaussian channel. And we can see that the thresholds here with the convolutional versions are much better. In fact, at 510, capacity is a half. So we're essentially at capacity with the 510. And same thing in the Gaussian regime. The capacity is 0.184. So we're almost there with the 510. So we get a significant improvement of the thresholds compared to the corresponding block code ensembles. And the reason for that essentially is this lower degree check nodes at the beginning of the graph. And we'll look at that in a different way when we come across this, when we discuss this more modern view of these codes in the next class.
It is a little different from what you see for block code. What is the reason for that?
That's the next bullet. Okay. The trend, no, we pointed this out also. As you go to higher density, with the block codes, you get worse thresholds. And we said that, well, okay, that's maybe understandable because you're gaining in distance when you increase the density. So there is this kind of natural trade-off between the strength of the code and the threshold you can achieve. When you go to irregular block codes, then you don't have as strong a code in terms of distance, but you get better thresholds, etc. So you have this trade-off lots of times. So we weren't so surprised, but we were surprised actually when we did this. So this is really nice. So we know with the convolutional versions, if we increase the density, we get stronger codes in terms of distance, which should give us, you know, better error floors or no error floor at all, better performance at high SNRs, and we also get better thresholds, which would give us better performance at low SNRs. So that's when I had that one slide, I think right at the end of class yesterday, that you have the regular LDPCs have good distance and good high SNR performance, but bad thresholds. The irregular LDPCs have good thresholds, but poor performance in the error floor. And the spatially coupled codes kind of combine the best features of both of those. Okay, the regular codes also have the nice implementation complexity because of the regular compared to the irregular. And the spatially coupled regular codes maintain that except for this small irregularity at the end. So that's why I say with LDPC convolutional codes, I've started using the term spatially coupled. It's interchangeable terms. There's not a need necessarily to look at different kinds of irregular designs because with the slight irregularity at the end, you kind of get what you want already. This first part, parity check matrices for LDPC convolutional, we'll use the terminology spatially coupled starting in the next lecture just because you'll see from the graph point of view, it makes some sense to use that terminology. These can be constructed from parity check matrices of LDPC block codes. I mean, this isn't the only way you can do it, but this is the way that it was first envisioned, such that you preserve the graph properties of the block code that you started with and you achieve a convolutional gain, okay, at least if you compare on the basis of the block length and the constraint length being the same. This is an old argument about comparing block codes to convolutional codes. What's the fair way to compare them? Is it equate block length to constraint length, or you do it at equal latency, equal complexity, and there's lots of different factors involved. So there's a efficient encoding complexity as possible with simple shift register based systematic encoder. Again, I say as possible. In general, you may have to tweak the matrix that you have in order to do this. Okay. And these codes, spatially coupled, you can use this high throughput pipeline decoding, which is a very nice architecture for high speed parallel implementation, but it does have a high decoding latency, or you can use the lower latency window decoding techniques. And these are all based on belief propagation. Okay, they're not optimal, they're suboptimal decoding methods. And we have large asymptotic distance growth rates, free distance in this case, because they're convolutional. And the capacity approaching, as we've seen, iterative decoding thresholds, and we'll talk more about this in the next class. Any questions on this then?
As we increase the density, there is a possibility of a shorter cycle length.
Yeah, sure. For a given constraint length, say, yeah.
What explains better reads?
Well, I mean that's a good point. I mean, you will in general, with increasing densities of matrices, if the other parameters stay the same, you will in general introduce more short cycles. But it's just that the help that the decoder gets from these low degree check nodes in the beginning of the graph overcomes that, basically. I mean, because you do wind up being able to achieve better thresholds even though you're going to higher density. So I agree it's counterintuitive. And that's why one of the reasons we were surprised when we saw it. It has been, now the work that we did was all numerical. We found these thresholds by density evolution. And that's why I say Rudy thought we may have made a mistake. And we thought we may have made a mistake also, because it was very counterintuitive. But his group has now proven this analytically, initially for the erasure channel, but now also for more general channels. So it is counterintuitive. Any other questions at this point?